Alright, let's say we want to know the equilibrium temperature of Venus. So let me draw Venus here. That's Venus. And of course Venus is going around the Sun, and the Sun is hitting Venus with radiation. So that is the Sun hitting Venus with radiation. But of course Venus is also radiating some of that back into space. So it's going to heat up, and it's going to radiate some of it back into space. So how do we figure out the equilibrium temperature of Venus? Well, we can use a simple energy rate balance. So that's going to look something like this. We look at the energy rate coming into Venus, and that's going to be equal to the energy rate coming out, because we assume it's in equilibrium. Now, what is going to be the energy rate coming in? Well, obviously we only have the sunlight hitting Venus, so that's going to be the only energy coming into the system. So, and that is going to be dependent on the intensity of the sunlight where Venus is. And we know the intensity at 1 AU, so that is 1 astronomical unit. That is equal to 1,400 watts per meter squared. Yeah, and we know also that the intensity decreases with this relation, 1 over r squared. And we also know that the distance of Venus is 0.723 astronomical units. So it's closer to the Sun than the Earth, obviously. So how do we find the intensity then of the sunlight at the position of Venus? Well, we can just say intensity at Venus. That's going to be equal to the intensity at 1 AU, times 1 over 0.732, and that is squared because we have the square here. Now, so we can write down for the energy input, the energy rate input. That is going to be the intensity at Venus, which is going to be equal to this. So we know 1 AU, intensity at 1 AU, times 1 over 0.732 squared. Times, alright, now because the intensity is over an area, times the area that is hitting it. So the sunlight is hitting an area, right? And the area, because the sunlight only is coming from that side, and well, it's going to look at Venus as though it's a disk, so we will only have to use the area of a circle, pi, and that is obviously pi r squared. And then we also have to account for the absorption factor. Now we know the albedo, that is equal to, for Venus, that is equal to 0.76. And the albedo is basically the percentage of sunlight that is reflected. So so obviously the thing that is going to be absorbed is going to be 1 minus that. So that's the percentage that's going to be reflected. So 1 minus that is going to be the percentage of, basically what stays in there. So that's times 1 minus A. We just see the albedo. I talked in another video about the absorption, but that's not the same. It's not the same thing. Now that is going to be the energy rate input. The energy rate output is given by the equation. Sigma, which is the Stefan-Boltzmann constant, times T to the 4th power, that's the temperature of Venus, which we want to know, times the area that Venus is emitting, and times the emissivity. But in our case, that emissivity is going to be equal to 1 because we have a planet, and well, this is something I probably have to memorize. The emissivity for a planet or a star is always usually 1. We can assume it's basically a black body. That has to do with how the atmospheres interact with the sunlight. But yeah, basically we can assume this to be 1. So now, and the Stefan-Boltzmann constant, that is also usually given as 5.776 times 10 to the negative 8. And yeah, now we write down all of this. So we substitute this for the input. Then set 1 AU times 1 over 0.732 squared times pi r squared minus a is equal to sigma t to the 4th times a e, and yeah, we just leave out the 1. Now we can just we'll write this in terms of t. So, well, we just divide here by the sigma and AE. AE, by the way, is going to be the area that it is emitting over, and this is going to be, because we have a sphere, it's 4 pi r squared. And if we substitute this into it, the pi r squared is going to cancel out. So we will end up with I 1 AU times this times 1 minus albedo divided by, well, the 4 stays, so that's 4 sigma, yeah, 4 sigma. Well, left a little too much space there, but we also have to take the 4th root of it, and that is going to give us the equilibrium temperature. It's the 4th root. We know sigma, we know the intensity at 1 AU, and we know the albedo, and that is going to give us an equilibrium temperature of roughly 229 Kelvin. And we are done.